In this lesson, we'll learn about ionization energy and its trend in the periodic table. Ionization energy is the energy needed to remove electrons from the neutral atom. This is a process called ionization, or to make an ion. In the periodic table, ionization energy generally increases across a period from left to right, as well as up groups from the bottom of a column to the top. Ionization energy increases across a period because atomic radius decreases across a period. A smaller atomic radius means that the electrons are held more closely to the nucleus, making them harder to remove. Ionization energy increases up a group because atomic size decreases up a group. Valence electrons of smaller atoms are harder to remove than electrons of larger atoms. However, as we'll see, there are some exceptions to these two ionization energy trends. In this graph, we can see the ionization energies of most atoms in the periodic table. Focusing on the first 4 rows of the table, or the first 36 elements, we can see there are a couple unexpected results. First, we can see that there's a decrease when going from elements in group 2 to elements in group 13. Secondly, we can see there's also a decrease when going from group 15 to group 16. Let's first see why ionization energy decreases from group 2 to group 13. To see why this decrease occurs, we must look at the electron configurations of these atoms. We'll use beryllium and boron as our example. The configuration for beryllium is 1s2, 2s2. Boron has one more electron, giving it a configuration of 1s2, 2s2, 2p1. From our rules of removing electrons, we know that in beryllium, an electron would be removed from the 2s orbital, while in boron, an electron would be removed from a 2p orbital. The 2p orbital is of higher energy than the 2s orbital, and thus it's easier to remove. This gives boron a lower ionization energy than beryllium. Let's now see why ionization energy decreases from group 15 to group 16. Once again, we'll look at the electron configurations. We'll use nitrogen and oxygen as our example. The electron configuration of nitrogen is 1s2, 2s2, 2p3. The electron configuration of oxygen is 1s2, 2s2, 2p4. As we can see from the configurations, nitrogen's 2p orbital is exactly half filled. This means there's one electron in each orbital. In the oxygen atom, however, there are 4 electrons in the 2p subshell, meaning one of the orbitals contains 2 electrons. Due to the electron-electron repulsion found between the 2 paired electrons, it's easier to remove one of them than it is to remove an unpaired electron from nitrogen's orbitals. This gives oxygen a lower ionization energy than nitrogen.